Hello, everybody. Welcome back. Today we are talking about the inverse trig functions in general, and we're going to start with the inverse tangent function. And you're going to see that this video will consist of a little introduction and discussion. What are the issues we run into? What are the things we have to consider in order to come up with this inverse tangent function? And then how do we apply it? How do we actually take the inverse tangent of various values? So that's the plan for today. So to start with, let's just recall the tangent function, and for that I'm going to pop over into my calculator Desmos. And in Desmos I already have graphed the tangent function. If I give myself a pointer here, the tangent function, it consists of a whole bunch of these. It repeating vertical stripes. They're a little bit, they look a little bit like an x cubed graph, but they're not exactly that. Similar shape, though. And the tangent function has these vertical asymptotes here. That's at pi over 2, and down here at negative pi over 2. And of course it has more of them down here at negative 3 pi over 2, and up here at positive 3 pi over 2. And etc. So it has a lot of vertical asymptotes. Those are going to be places where the function is undefined, but that's just fine. That doesn't bother us. The thing that we're interested in is as follows. I want to talk first about just reminding you what is the idea of an inverse function. So a function itself, for example, tangent x is a function. The way that that function works is that you plug in a value for x, that's like the input, and when we do this on a graph, we look at the x-axis when we plug in an x, and the function is asking the question, okay, if we plug in a number, for example, this is pi over 4 right here. If we plug in pi over 4, what do we get? What is tangent of pi over 4 equal to? And the answer is if x is pi over 4, we go up until we hit the function, and we see that it comes out here, and it's exactly equal to 1. So tangent of pi over 4 is equal to 1. If it helps you to think in degrees, the pi over 4 degrees, if we were working in degrees, would be, pi over 4 radians would be equal to 45 degrees, and a 45 degree angle is when the tangent is equal to 1. Okay. So the basic way that we work with this graph is you give me an x to put in, that's like putting in an angle, and then it tells you on the y-axis what the output, what the tangent of that angle is equal to. Now, when we look at inverse functions, what we want to do is kind of the opposite. We want to say, okay, if I know that the tangent of x ends up being equal to this number right here, say 2, then what angle was the x that I put in to begin with? And the way that you would answer this is you would go to the output, the 2, you know tangent is equal to 2, and you would trace it back horizontally to the function and look at what is the x that you would have to plug into the function in order to get 2. Here this x is between, let me say that's pi over 4, and that's pi over 2, somewhere between pi over 4 and pi over 2, right there. Yeah. Of course, the problem is that that's not the only place that you can plug in that gives an output of 2. For example, over here, if we follow that line at height 2 over to here, there's another answer here. It's bigger than pi. It's right between pi and a quarter and pi and a half. Right in here, there's another angle you can plug in that also gives an output of 2. And in fact, if you trace over this direction, there's another angle that gives an output of 2. This angle right here between negative pi over 2 and negative pi over 4. This angle right here also has an output when you take the tangent of it of 2. So it's sort of like when you ask what angle gives a tangent of 2, the answer is there's lots of different ones. There's one here and here and here and here and here, and they go on and on. And what this says, this example says that there's no single answer to that question, the question of what angle gives a tangent of 2. And that's reflected in terms of our ideas about functions in the notion that the tangent function is not one-to-one. That is to say, you can draw a horizontal line, and it touches that graph, it crosses that graph in more than one place. So we say that tangent fails the horizontal line test. Since it fails the horizontal line test, we can't create an inverse function. And it's exactly for the reason that I sort of just illustrated. If I give you an output for tangent, the output of tangent is 2, well, and I ask you, which input did you give me? Well, there's a lot of different answers. And since there's a lot of different answers, it's no longer, the inverse would not be a function. It doesn't give you a single answer. Okay, how do we solve this? Well, what we can do is we can take the tangent function, and instead of looking at the entire picture of the tangent function, we can restrict ourselves to only one chunk of the tangent function. And you notice the tangent, it consists of these repeating sort of S-shaped stripes. We're just going to look at one of them. We're going to look at the one that's right here. And to do that, what we want to do is restrict our x's so that they only cover the part of the x-axis which includes this part of the tangent function, this chunk of the tangent function. It's like one repetition of the tangent function, the one that crosses the origin. So we're going to delete all the things over here, delete all the things over here, and just look at this one. And how do we do that? Well, we can do it by taking our tangent function and adding a restriction to that. In Desmos, we can do it by putting it in curly brackets afterwards. What do we want? Well, I happen to know that the places that we're going to restrict it to, over here, there's an asymptote at -π/2. That's going to be our beginning place. And then up here, there's an asymptote here at π/2. So we're going to go from -π/2 to π/2 on the x-axis. And we do that as follows. Let me see. Negative, to put in pi, I just type pi, and then divided by 2. And we want to make sure that that's less than x, and that x is less than π/2. This is going to bound our x's, everything between -π/2 and π/2. So pi... It'll look a little funny until I get the whole thing typed in there. I thought I was using a bound of pi, but really I want π/2. Great. So this is the tangent function, but restricted. So it's basically exactly like the tangent function if you look at inputs between x equal -π/2 and π/2, and then it's just blank everywhere else. Now, things to notice. By restricting the tangent function in this way, we now have a one-to-one function. This thing passes the horizontal line test. If I draw a horizontal line anywhere on the screen, it's only going to touch this function once. This tangent function, this restricted tangent function, it has domain on the interval -π/2 to π/2, and the range includes all the real numbers. It goes all the way down here and all the way up here. And since this is a one-to-one function, it has an inverse, and the inverse is obtained just by taking every x and y value and switching them around. Yeah. So, for example, I happen to know one value of tangent is π/4, that's a 45-degree angle. Tangent of π/4 is equal to 1. So this point right here has coordinates, the x is π/4, and the y is 1. Okay, if we look at the inverse tangent function, it's going to switch all of the x's and y's, and so that point is going to be switched around with the point that has x coordinate 1 and y coordinate π/2. The point 0, 0 is going to go to the point 0, 0. This point, which is pi, it's a little bit less than 90 degrees, which means a little bit less than π/2, and the output is equal to 2. The y is equal to 2, is we're going to switch that, and we're going to have an x of 2 and a y of that π/2, a little less than π/2. What does this function look like, the inverse tangent function? Let's take a look. I've typed it in already, so I just have to turn the graph on. Okay, some other junk in there. Here is what the inverse tangent function looks like. It is in black, and you can see that that function in black, first of all, it's a function. That means it passes the vertical line test. It's also a one-to-one function. And every xy on the original function, the blue function, has a corresponding point if you switch the x and y values on the inverse function. So this is the function that we call inverse tangent. And if you want to ask a question, for example, what angle has a tangent equal to 2, then you could plug in 2 now on the x-axis, not 2 pi. Remember, it's a little strange because we measure angles with the pi's, and for the inverse trig function, the angles are now on the y-axis, and it's the tangents on the x-axis. So you would need to find this 2 pi, 2 times pi, pi is 3 point something, 2 pi is 6 point something, and we want about a third of that, so it's somehow in here. This is where the number 2 is on the x-axis, and if you plug it in, the answer it will give you is the number on the y-axis, which is exactly the angle you would have to plug in to get that 2 from your tangent. Okay, let's go ahead on back. And let's take a look at some examples here. Now, before we move on, I do want to make one observation. First of all, the inverse tangent function, it's written like this, tan with a little -1. That's the inverse tangent function, and this is terrible notation in the following sense. It looks like we're raising something to a power here, but no, that little -1 just means inverse tangent. That's all that it means. So don't try to think of this as a power. That will mess you up. There's another notation. The inverse tangent is also written as arctangent, arctan of x, and some people prefer this version because it doesn't have this confusing thing that looks like a power there, but it just means the same thing. When you plug something into this, what you're asking is, if tangent is equal to that thing you plugged in, then what was the angle that we started with? What angle has tangent equal to this? That's the way to interpret the inverse tangent function. And the general idea behind the inverse tangent function is if you have y equal to inverse tangent of x, this is sort of the same as saying that the tangent of that y, the y is like your angle here, the tangent of y is equal to x. So when you write inverse tangent of a number, what you're asking is what that thing is equal to. What you're asking for is what angle do I put into the tangent function to get that x out. So this is just a reflection of the fact that this is the inverse function. This inverse functions always switch the inputs and outputs with the original, from the original function. Okay, and the sort of observation part 2 is that the tangent has this nice property. The inverse tangent is what we call an odd function. I don't mean that it's a bizarre function. Odd functions are something that were covered earlier in the semester. If you don't remember, a function is odd if when you plug in a negative number, you get the negative of when you plug in the positive number. So this function is odd if f of -2 is the negative of whatever f of 2 is, for example, using 2 as a possible input. And if our function is inverse tangent, then the way that this looks is that the inverse tangent of -x is equal to the negative of the tangent, the inverse tangent of x. And this observation is going to be helpful to us, especially if we happen to know the value, the inverse tangent for a particular input, and now we want to know the value of the inverse tangent for a negative of that input. Well, we just make our answer negative. All right, if that seems confusing, we're going to see how it works in just a second. So let's go ahead and look at some examples. The example I'd like to look at is this one. Use the table above. This is just a table that shows the trig functions, not the inverse trig functions, but the original trig functions for various angles. This shows sine x, cosine x, and tangent x, and they're just the common angles in the first quadrant. So 0, 30 degrees, 45 degrees, 60 degrees, 90 degrees, or in radians, 0, pi over 6, pi over 4, pi over 3, and pi over 2. Okay. This is a table that should be in your head, and if it's not too late to put it there. Spend some time thinking about it, and there are many sort of interesting symmetries and connections between parts of this table that make remembering it easier, but I will not get into those here. Okay. When we plug something into the tangent function, so we're going to be looking at 2 rows of this table, the x, which represents like the angle here, and then the tangent of x. That's what that tangent of that angle is equal to here. And normally, when you work with the tangent, you think of an x, and then you look down and you see what the tangent for that x is. So for example, if our angle is pi over 6, or 30 degrees, the tangent of pi over 6 is radical 3 over 3. Now, when we do the inverse, it's like we work the other way. We switch the inputs and outputs. So now, when we're plugging something into the inverse or the arctangent, we're going to be thinking about plugging in this guy and then looking back to see what angle it came from. So let's go ahead and do this as an example. Whoops. Boop. And it says find exact values. That means that we're not going to be using a calculator and getting decimals, but instead we're going to just be using this table and a little bit of thinking in order to give us the exact values. So let's go ahead and do it. So this example A is arctangent of 1. Remember, arctangent just means the same thing as inverse tangent. And we're saying, what angle do you have to use in order for the tangent to give you a 1? Well, we can answer this by saying, all right, where is the tangent equal to 1? The tangent is equal to 1 here. I happen to know the tangent is equal to 1 at a 45-degree angle, or at pi over 4. And you can see here tangent is equal to 1, and that happens at pi over 4 if we're in radians, or 45 if we're in degrees. This says give the answers in both degrees and in radians, so we will give both. The arctangent of 1 is equal to pi over 4, or 45 degrees. And we're done. There's no more to show. This is just getting used to the idea of the inverse tangent or the arctangent. That's it. I would give the next ones, B and C, a try. Pause the video, see if you can come up with answers for them now, and then go ahead and play again, and we'll work them out together. Okay, let's take a look at B. For this one, the arctangent of minus radical 3 over 3. Well, of course, in our table, we don't have minus radical 3 over 3 here, right? Because it's not one of our first it doesn't come from an angle in the first quadrant. But what we know is that the tangent is an odd function, and that is to say, if you have a minus on the thing that you're plugging in, that's equal to what you get if you just move that minus out in front. That's the negative of the arctangent of radical 3 over 3. This is using the observation just above this observation here. And of course I'm saying arctan instead of tan inverse, arctan instead of tan inverse, but the principle is the same. Now, question, what is the arctangent of radical 3 over 3? Well, radical 3 over 3, that's one of those outputs of the tangent function that comes from a common angle, and that common angle is 30 degrees, or pi over 6. So the answer to this, we're going to be careful. We have a minus in front of the arctan. So the arctangent of radical 3 over 3 is equal to pi over 6, but since there's a minus in front, we put that minus there. Alternatively, if we're in degrees, it is going to be minus and 30 degrees. Okay, that's our solution for part B. Let's take a look at part C. The inverse tangent of 0. Well, what angle do you have to plug in to the tangent function in order to get 0? And here, the tangent is equal to 0 when the angle is 0. And it happens to be 0 in both degrees and in radians. Here I just use the other notation, tangent inverse, instead of arctangent, and that's just because I want you guys to get used to using both of them. That means the same thing as arctangent of 0. And that's equal to 0 degrees or 0 radians. That's it for arctangent. You're going to have a chance to apply these ideas in the homework, so take a look, and if you have questions, feel free to contact me.